geometry of curves, non-archimedean SYZ fibration. So let's start with the basics of Berkovich spaces. We fix K, a complete discrete valuation field. So the theory works also in the non-discrete valued case, but due to time constraints, let's restrict to the discrete valued case. So we have a valuation map from K to integers plus infinity, and we also have an absolute value given by the valuation, absolute value on the field K goes to positive integers, which send an element A to exponential of minus valuation A. So absolute value is just the exponential of valuation. Valuation, absolute values, they are exactly the same thing. Okay, so introduce some notations. Ring of integers we denote by K0 consists of elements A in K whose valuation is greater or equal to 0. And maximal ideal is same thing, but greater than 0. And then we can take a quotient residual field K tilde denoted by K tilde is the quotient. So if you are confused, let me give you some examples. The Laurent power series field, we have a valuation map from K to Z union infinity that sends a Laurent power series, formal series, AITI, to the mean the first I where the coefficient is non-zero. And we have a ring of integers the power series field, maximal ideal generated by T, and residual field is the field of complex numbers. Okay, so another example, p-adic field. Yeah, I hope you know what the valuation is. And we have a ring of integers is just ZP. Maximal ideal generated by P, and the residual field is FP. Yeah, just for exposition. Okay. Yeah, many things works in the non-discrete case. I guess every time we have to ask, will it work in the You can ask every time when I state something, and I can explain that. So now let me explain what is a Berkovich space over K over such a discrete valuation field K. It's a bit complicated to explain in the general case. Let's still limit to a special case that is Berkovich spaces coming from algebraic geometry. So we have, let's say, general Berkovich spaces. And over K, And we have algebraic varieties. Over K. We have an analytification functor, goes there. Analytification that sends an algebraic variety over K to a Berkovich space over K. And let me just explain what are Berkovich spaces lying in this circle. So, yes. So what is this X analytic? This X analytic is a locally ringed space. As a set, so first, as a set, it consists of points which are pairs psi this guy, such that psi is a scheme point of X and this is an absolute value on the residual field K psi extending the absolute value on the ground field. So this is as a set. Then we put the topology. Oh, so for psi, like any closed point, then we know that there exists a unique valuation, absolute value extending the one on the ground field. The interesting happens when psi is not a closed point, like prime ideals which are not maximal ideals. Yeah. So topology, what the topology we put? We put the yes, yes. Where we get like most interesting points of the Berkovich space. We will see these points later. So topology, we put the weakest topology such that first we want the map to be continuous. It's just the map forgetting this part. Just take psi, forget the part absolute value. This is continuous. And second, we want a norm of pullback of any regular function right here. Regular function on any Zariski open U inside X is continuous on the pre-image of U by R. So just says that if I take any function, like regular algebraic function on X, then I consider it as a function on the analytic space, and then I take norm of this function everywhere. We want this to be a continuous function.
So if psi is a closed point,
Mm-hmm.
then
You know how to map that to X plus
no. Sorry. Then what is my choice of the iteration?
No choice, unique.
Because k of psi
not k. K of k is a finite extension of k.
But if it's the generic point, then I have a lot of choice.
Yes. Yeah. So, okay, and we just put the weakest topology so that for any meaningful function, we take norm. It's analytic geometry. When we take norm, we get a continuous real-valued function. Okay, and then what else can we do? Theorem of Berkovich. So with this topology, then the analytic space X analytic is locally compact and locally path connected. One can also show that X analytic is connected if and only if X is connected. And similarly, X analytic is Hausdorff if and only if X is separated. And X analytic is compact if and only if X is proper. So, like we have analogs in the complex analytic setting. To make it locally ringed space, we still need a structure sheaf. O of X analytic, that's very easy to define. It just consists of convergent power series generated by functions on X. So let me give an example, the simplest example for analytification. We take X to be the algebraic torus over K, which is spec of algebraic torus, spec of this guy. So we can consider its analytification by the analytification functor. So this is a nice GM, sorry. When we have functions, we can make power series. Just to take some functions and then take some like power of these functions. Yeah, for example, when you have x1, x2, you can take some like x1 to the power 1, x2 to the power 3 plus. But you can take infinite sum. Yes, yes. Yeah. Yeah, it's just not completion. It's less. You need convergence.
But the point is that convergence involves absolute value, and that's why it's on X.
Yeah. It's less than. No, it's. Yeah, maybe one. You can say that. Yes.
But I mean, you could just, power series, you could just say series, right?
Yeah.
I mean, you could say, well, let me look at the series 1 plus 2 plus 3 plus 4 and so on, but that's not convergence, so I'm not going to do that. So the nth term doesn't have the value. Every term is a function.
Yeah. So that's the simplest example, and we can play with this example. We can define a map pi from X analytic to Rn, which is given by X goes to valuation of T1 of X to valuation of Tn of X So we get a map from X analytic to Rn. And let me just say what it. Yes.
So can we see what that looks like at the non-closed point?
First, maybe just for people who are confused by this notation, valuation of t, let's say of ti of x, what it means. So I said that valuation, absolute value, they are the same thing. So that's minus log of the norm of ti of x. And let me explain what is ti norm of ti of x. We know that x is some absolute value corresponds to a scheme point plus an absolute value on the residual field. So this ti norm of ti of x is essentially we take ti, we restrict the ti to the residual field and take the corresponding norm given by x. Just some rewriting of the formula. Yeah, I hope. Did I also answer your question? No. For the generic point, it's the same.
But let's take an example of what is O.
So for generic point, then you have Kasai generic point, and this guy.
But what's the set absolute values on the generic point?
I will describe all the points.
Okay.
Yeah. So, yes. So I hope that also answers the question of Alex. Not yet. Let me. So define a map F from a Berkovich space X to a topological space B is called an affinoid torus fibration if locally on B it is of the form just a second. So this is, I'm sorry here, it's very small. I will read. Yeah. Yes, Paul, what was your remark? Oh, let me call it Y. Yeah. So I define a map from a Berkovich space Y to a topological space B. This such a map called an affinoid torus fibration. If locally on B, it is of the form this pi. So we take U open in Rn and pre-image. Yes. So I hope this now answers the question of Alex on Monday about what is affinoid torus fibration. It's just as simple as this example. So now that's torus.
It's built out of glue in such things.
Yes.
A cover of the base. Once you say you have a topological space which might be manifold, real, and then it's a manifold, and you take an open cover, and over an open cover, you have
implicitly you say that your Berkovich space looks totally like that.
Yeah.
That's always the case.
That's not always the case. But in the case of, that's definition for an affinoid torus fibration.
And remind us, in SYZ, this will be what you will have away from the singular.
Yes, exactly.
So that's a statement also about one.
Yes. Yes. No, that we can do it in general. Define it in general.
It will locally look like.
What's the fiber of pi?
I think that's exactly what
Fiber of this map. like points whose norm is fixed. Yeah, I will describe the points.
Yeah, but I think he's still owing us an explanation of what
Yes.
the points of X and for
Yes.
We started by, so for simplicity we were assuming that this is a discrete value.
Yeah.
So in this case, is this map from time condition to R, is it actually kind of surjective?
It's always surjective.
How does one?
Because there you get everything.
Yeah, but on the closed points.
No, closed points, it just maps to Q. Then you have to add other points. Mm-hmm.
Maybe.
yeah,
but he's not gonna tell us. So
Now I'm telling now. So in order to you all asked me how can we understand better the underlying topological space? Yeah, this absolute value is not necessarily discrete.
That's right, but again, I'm only used to thinking of the closed points.
yes.
But on the closed points, as you said, you only hit Q.
Yeah.
So I'm trying to imagine how do you then get all on R?
I mean, the quick comment is the classical symplectic geometer's wrong perspective on this is you start with something other than record field. You have continuous valuations. You only care about closed points. And then basically it is the valuation map from something that locally looks like Novikov field to the n to Rn by just taking the valuation of each component. This is not what we are doing.
Yeah, so as you already remarked that like if we only take closed points, we only get Q. So like for because when you make a finite field extension, you get fractions.
Yeah, but I'm ignorant of closed points, so I want to know how.
For closed points, its residual field is a finite field extension of
Can
the.
I see an example of a point that goes to 1/2, for example?
It just take
I mean, there's KT, right?
yeah
So you can ask for
t squared equals
T squared equals
t. Yeah.
I mean, if K is a function depending on the Q,
Yes, of course.
then
It's a single
T1
point
squared
equals.
equals Q.
I see. Since we don't have fractional powers, we add them there.
Mm.
Sorry. Just again. So these things are not algebraic equations.
K is not.
It cannot be because of what.
Yeah. Yeah.
Like equation.
Yeah.
Let's pretend that this.
We will see that discrete evaluation.
The statement because it's a discrete valuation field is not sufficient.
We will see discrete evaluation is simplifies lots of things because for a non-discrete valued field, when we take a ring of integers, it's not noetherian. The ring.
But on the other hand, if it's non-discrete, then you can assume that it's
Directly closed.
But that doesn't help many things. Yeah. So as you remarked that like when we only consider closed points, we just hit Q, and people always have the impression in non-Archimedean geometry that things are totally disconnected, like not much intuition in non-Archimedean geometry. And it was Berkovich, he first suggested to consider all valuations, not necessarily like all these points. And he said that he was really excited that he discovered all these hidden points of the geometry. Yeah, so in order to better understand the hidden points, we will use a tool called models. So we can better understand the underlying topological space of a Berkovich space using models. So what do I mean by models? Let X, we fix X, a smooth proper variety over K. So definition, an SNC model curly X of X is a regular scheme. Yes, flat and proper over the ring of integers K0 together with an isomorphism between the generic fiber of X, of curly X to X. So I write generic fiber defined by base change. So we want an isomorphism between the generic fiber of curly X, X eta, to X, such that the special fiber XS defined by base change to the residual field is a simple normal crossing divisor. On the total space, curly X. Oh, that's too bad. No, that's like Boolean either 0 or 1. Yes. Such that, yeah, did I write? Such that, and such that XS, which is the special fiber, is an SNC divisor. Yes, we will. I prepared an example for this model. Just the notation. Eta is just the notation. So X eta just means you make base change to the generic fiber. So yes. So if you think, you can think of K0 as a small unit disk, and X eta is you take the fibers over the punctured disk, and XS is the fiber over this 0 point. Yes? Oh, what? This model? Sure. I mean, like the correct way to work model for Berkovich space is to work with formal model, not algebraic model. Like I always work with formal models, but it takes time to explain. So now I will give an example of of a SNC model. So that will be a running example. K3 surface. We take C to be the Laurent power series field. It's the same. You just remove some variables. Yeah. So I consider first the space in P3 over K0 given by equation x0, x1, x2, x3 plus tf x3 x0, thank you, where these they are homogeneous coordinates on P3. And just a second. And F is a homogeneous polynomial. Say generic homogeneous polynomial of degree 4. Yeah, I already assumed K to be the Laurent power series. Yes, over C. Yes, Paul, what was your question? Yes. Yeah. Okay, so yes, but this X0 is not yet an SNC model because it's not regular. So X0 contains 24 conical singularities. We can. Oh, you just compute the derivative.
So you're saying at non-zero values?
At 0, central fiber.
Okay, K0 is C double bracket T.
Yes, yes, yes. So X0 has 24 conical singularities, and we let X to X0 just blow up the 24 points. I don't do base change. So you don't get rid of by doing base change, but we get rid of this by making blow-ups. And now this is then X curly X is an SNC model of the generic of its generic fiber. Okay, so now I'll describe a construction which generalizes that construction to the global case. So we will given curly X SNC model of straight X, and let DI be the set of irreducible components of the special fiber, but with a reduced scheme structure. So then we can define Calamus polytope to be S curly X consists, it will be a subset of positive real line to the power I, and it consists of points AI such that the intersection of DI is non-empty when for all I where AI is 0, and sum of MI AI equals 1, where MI is multiplicity of DI in the special fiber XS. It's maybe difficult to pass for you, but as an abstract simplicial complex, this guy is just isomorphic to the dual intersection complex. As an abstract simplicial complex, this is isomorphic to the dual intersection complex of the special fiber. Yes, yes. So running example. For our K3 surface, we have this equals first tetrahedron, and then for every edge of tetrahedron, we have 4 triangles attached. So yes, that's because I blow up some points there. So totally we have 24 triangles. Each blow up of each conical singularity add like P1 cross P1 in the total space. Yes, that's a very good remark. We will see, like when we talk about, we will see where a small resolution happen in a moment. I will modify this. Yes. Now we just do a naive blow-ups.
And the tetrahedron is just the faces of the tetrahedron, right?
It doesn't have interior. It's two-dimensional. Okay. So yes. And we see that each vertex. You have another question?
Oh, I see. So this is embedded in like R to the 28 or something.
Yes, exactly. Yes.
Well, you defined it like that.
Yes, I defined it like that, embedded. Clemens polytope embedded. The Deuce intersection complex is abstract. So here it's embedded. Each vertex, yes, yes. Yeah, so, oh.
I think I need another explanation again
For?
why this Clemens polytope is vertical in the case of the case system.
Oh.
So the central fiber, like if you hadn't done the resolution, would just be x0, x1, x2, x3 equals 0, the usual tetrahedron. It's four CP2s intersecting in a configuration of the tetrahedron. So the dual intersection complex would note that they intersect, three of them intersect at each vertex of the tetrahedron. There are four special points in your singular case space where three CP2s intersect. They correspond to the faces of that tetrahedron. Because then you can look at linear combinations with coefficients summing to 1 of three CP2s that intersect. Now, that's before you do the blow-ups. If you do blow-ups of the 24 base points of that family, where you had quadratic singularities, then you actually added, and on top of that, P1 times P1s that set basically on the edges between two of these CP2s. So now you have triple intersections between an exceptional P1 times P1 and two of initial P2s. And these are the triangles sitting on top of the edges.
P1 times P1 is flowing over 3 dimensions.
So there's four triangles on each edge of the.
Yeah, thank Denis for the explanation. So each vertex of Sx corresponds to a divisor, since it's, by definition, corresponds to a divisor di. And when we have a divisor, we have a valuation given by the divisor on the algebra of rational functions. Valuation on. So that was the question of James, maybe.
So is it the divisor gives the value? Oh, by looking at the order of vanishing
Yes.
of the divisor.
So we get a valuation on the on the ring of rational functions, like the most.
It's a discrete valuation.
Yes, yes.
We can maybe more detail about what is, how does it extend the valuation of K? So is it the sum, is it by combining the valuation of the coefficients and the valuations of monomials, say?
Yes, we don't change the valuation on the background.
For example, to be concrete on this case, in the divisor say x0, we would give valuation x0 equals 1 and valuation t equals 1.
Mm-hmm.
Okay.
Mm-hmm. Mm.
I'm saying if we take the divisor corresponding to x0, then we should have k of x should have, did I mean x0 or did I mean the others? No, I'm confused. Sorry, we have valuation of the whole coefficient field, right, which should involve x0, x1, x2, x3, and t.
I mean, all he's saying is it extends the valuation because if I look at what's the order of pole of the function along this divisor, and if I multiply the function with t, the order of pole is going to go down by 1
Mm-hmm.
because 0. So this valuation automatically extends the valuation of the field.
Okay.
Yeah.
Thank you. That's much
Yeah.
better.
So yeah, I think it's without the formulas, it's
The
better.
question was, why does this valuation extend the valuation on the ground field?
Yeah.
Right, so let's take case equals CT, right? So for the valuation is the T has valuation 1 and so on and so on. So I take this model and I look at this divisor that's inside the target 0, and now I look at functions and what is the order of poles of the function.
The order of zeros.
That's what is happening.
Order of zeros.
Order
Yeah.
of zeros, yes. Yes, order of zeros. And then if you multiply a function by t, then the order of zero goes up.
Increase,
by
yes.
one, right? You can complete that concept. What if the divisor is not decreasing? Yeah, it's not allowed. Because it's simply continuous.
I think we're just looking at the vertices, which means the elementary definitely big. Yeah.
No, but Paul's saying, if you have something that's
No,
defined by
di
squared equals
di by definition is the with reduced scheme structure. Yeah. So here we still get so when we have a
Valuation is just order of vanishing along the I think maybe.
I think also it's asking to just stand out the sentence that's
given maybe given by order of vanishing at di.
That's the only thing to work.
you wrote K parentheses there, so this means kind of illustrate.
Yes, yes.
So vanishing or pole.
Yeah, pole is negative, then you get.
Pole is negative. It's the same convention when you say order of vanishing.
No, I don't see any contradictions here. It's fine. Oh, has so yeah, order of vanishing. So it's compatible with the evaluation on the base because on the base it's also order of vanishing, right? So okay, so yeah, so here just for single divisor I, then theorem of Berkovich says that this extends to a canonical embedding from the Clemens polytope to the analytic space. So here we already know what for each vertex where it goes, and the Berkovich says that actually we can embed the full Clemens polytope into the analytic space.
But that's not very surprising.
That's when everything's worked out, it's not very surprising. But
On the example, it's not surprising.
on the example, I didn't really define how Rn embeds into X analytic.
No, but it's
Yes.
combinations.
Yes.
To make sure I'm understanding this given by the order vanishing at di. So the reason why it's compatible is because this di lies in the special fiber of
Yes.
0 in
Yeah.
in family. So
Yeah.
Yeah. So in particular, T vanishes to order 1 in the
Yeah.
X product.
Yeah. So Berkovich says that we can extend just by linear combination, and moreover, there exists a canonical strong deformation retraction from X analytic to the Clemens polytope. Now, maybe, oh, you have more questions.
What is canonical? I mean, is the retraction canonical, but it's been mapped from X analytic to
The whole deformation process is canonical.
also canonical.
Yes.
What's the retraction?
It's all about elementary topology.
The topology. So for example,
Oh.
can we see at some point how the closed points talk to the general
Yes,
point?
yes. So, yeah, I will explain more about the topology. So maybe let me first give you an idea what is this retraction. So remark, the retraction map. Let me just explain the final moment of the retraction. The retraction map tau from X analytic to X to the Clemens polytope has a simple description. So we know that locally maybe I write in this order. For each divisor di, then locally on curly X, such a divisor is given by a function, defined by a function ui is given by a function ui up to multiplication by invertible functions. Okay, so then we just take valuation of the function ui of x. This is a continuous function. On the analytic space. Now the tau, so tau that goes from, we define tau goes from x analytic to r to the power I given by x goes.
It's a function with values in what? Function on
Just a second. What was the question?
So if I take the point x to be on the divisor,
No, there's no point. X is a point on the analytic space. Yeah.
wait, the analytic space contains. Oh.
At least that is generic fiber.
So basically, you have this variety of the space that's over C, the double curly bracket T. Now we have this model. A point over a section. And that is going to tell you how to map it to the coordinates. How fast does it go? Which divisor? Which sections divided? That's going to tell you where we transfer the
I see. So if the limiting point is in the divisor, that I will notice because that's how the values move in on the divisor. If I take a section that passes through one of the components of the space, then those values should be visible in the section.
So the image of this map coincides with the Clemens polytope defined there. And now we have, once we have this, we can get.
Well, it's contained, you think that's obvious.
Yeah, yeah. So now we can have a better understanding of the topology of Berkovich space, the theorem of Kontsevich and Soberman. I just finished write the theorem.
Yes, if it's not a C double bracket T point, but it's a point that lies over some extension, then it will be a multivariate section.
And point that oh yes, okay.
Because you've got fractions.
Yes, okay.
It's a
Thanks.
multivariate
I see. So what you do is you base change multi-sections formally, and then that's how. I see. So if I take something that's say the intersection of two divisors, I would have something that's ranked order 2 section going there, and diagonally etc. on the product of the two functions, and then I can base change it, and then I will get to basically 1/2 the order dimension. Because I've done the base changing to make it a section instead of convergence.
But you could have gotten some other number, right?
Yes, yes, by changing the order. Well, I can get the rational terms. I don't have to get the real terms.
The claim was not that you get the real points from closed points.
We haven't seen any close points.
Sure.
And non-close points.
That's quite a different question.
Oh, we see all the no the this
We don't
this
have any examples in our mind.
oh this example this embedding it goes to non-closed points.
Not an example.
Ah,
Yes.
okay.
So you're saying it's tautologically onto because the embedding. I mean,
Wait, what's it
if you have the embedding Sx into Xn, and that gives you the retraction.
Yeah.
It's onto.
Yeah. So now we get a better like just a mental picture for what a Berkovich space look like. Assume a residual field has 0 characteristic, then the analytic space is homomorphic to the limit of Clemens polytope over all SNC models.
Limit under what?
SNC models. So SNC models they are
How do you relate them? I mean, under what?
SNC models they are ordered by blow-ups. So when we have 2 SNC models, we can always like blow up and then blow down. When we make blow-ups, we make changes to the Clemens polytope, usually add more wings there. So Berkovich space is limit of adding all possible wings to this.
So limit in that direction, where you start putting
More and more wings, yes.
What does the Berkovich spectrum of the elliptic curve actually look like?
Yes, that's
Circle with the
of elliptic curve with a bed reduction. It's a circle. Yeah. A circle with, then we start to add wings. So it's like with all these trees growing. Type 2 points called. Oh, so depends on your ground field.
You could say if we do it of, say, C brackets.
Like we did the same, we did something in P3, I did the exact analogous thing in P2 with the
Then it's just a rational points. Yes. All branching happens at rational points because you see it from the theorem. The branching comes from the blow-ups, and you can only blow up. Yeah. But it's yeah. So up to now it.
But you see, after you blow up, it's not a triangle anymore. It could be four.
Yeah.
So that's why. That's why exactly like which point. You should imagine it's a circle with its rational points being distinguished. That's the maximal way to subdivide.
so it's like a grid.
Yes. So up to now, my talk has nothing to do with Calabi-Yau, and now we will introduce Calabi-Yau condition. So second part, non-Archimedean SYZ fibration. We see that the Clemens polytope, by definition, obviously depends on the choice of the model curly X. And in the case when X is Calabi-Yau, actually we can get a canonical sub-complex of this Clemens polytope, which doesn't depend on the choice. So let me explain. Assume, again, residual field characteristic 0, algebraically closed. Then X Calabi-Yau, which means canonical bundle is trivial. So we fix omega is volume form on X, non-zero section of the canonical bundle. Definition by Kontsevich and Soberman is that for each divisor di as above, we define as before, we define weight of di to be we compute the order of the volume from omega along the divisor di and divide by the multiplicity of the divisor di. So we define this weight and rational number. Yes.
You still didn't quite tell us how the closed points came into this picture. So should I imagine that if I had a closed point, which maybe if I was over this example of C,
Mhm.
series in T, might have come from a section of my fibration.
Yeah.
I mean, the points that you give me in the compressible example, I'm supposed to think of instead doing blow-ups. So can I imagine that maybe there's a way to turn such a section, which came from a closed point in the general fiber, and turning it into a divisor, which is...
No. It only happens, the closed points, they are included only by the limit. At each finite step, you don't see any closed point.
You think the closed points should be the ends of
Yes,
this thing?
they are ends of the tree.
But the tree has ends?
Yes. No, ends, just the point. Points. Yes. Yeah.
So basically, it's a little bit like Puiseux expansion. I mean, I take
Close
a
the points.
section and then I look. I mean, if I have a section, how do I figure out where it ends up on the tree?
Ah.
Keep blowing up.
Yeah, you see.
Nothing more happens.
Yeah.
And then I will see where it ends.
Yeah. But not all ends are closed points. There are ends which you keep blowing up, but finally you don't reach a closed point, but you end somewhere in the middle. Yes. So we have definition, and di is called essential if Wt weight function achieves minimum at di. So let yes.
Information is because I can multiply omega by t or something, and then
Yeah.
orders shift.
Yeah, you can multiply so that minimum is -1, for example. Let be the subcomplex. Simple normal crossing, the divisors, they are not necessarily reduced. The special fiber is not necessarily reduced. They are, otherwise it's called semi-stable if it's reduced.
The fiber of like x equals to x squared is simple normal crossing.
Yeah, x squared, y squared, z equals t is simple normal crossing. Yes.
Okay.
So let this be subcomplex spanned by vertices corresponding to the essential divisors. So we define the image of Sx essential under the embedding of the Clemens polytope to the analytic space is called the essential skeleton.
Is there a minus sign in this one, or do you mean max?
Order. So I want divisors with maximum order of 4, then it's minimum order of
Order is now the order of poles, because before it
order 0. Always here it also means order of 0. But I want
So is the pole counting negatively or positively? If I have a pole...
it's negative. So I want maximum order of pole at essential divisors, which means I want minimum order of 0.
So basically, if you blow up, you get something on which it vanishes more,
Yes.
but you don't want those.
Yes, yes.
Okay.
Yeah. called essential skeleton of X, denoted by Sk of X. So now theorem by Kontsevich-Soberman, Mustata-Niguez, is that this is independent of the choice of SNC model curly X. So our running example, in the case of K3, the essential skeleton is just the tetrahedron inside. We ignore the wings. So this essential skeleton will be the base of our non-Archimedean SYZ fibration, but we do not yet have a retraction map. We had retraction map to the Clemens polytope, but we didn't have, not yet have to the essential skeleton. In order to get a retraction map from the analytic space to the essential skeleton,
If I take the tropical variety defined by the equation and consider it bounded part, is it always going to be this essential thing?
where is it tropical?
So just think of that tropicalize that variety.
Mm-hmm.
In your case, for example, making you get a tetrahedron with something sticking out.
Yeah. I just consider Clemens polytope.
But if I don't, if I do the tropical, if I consider tropical variety.
It's not embed. You have to tropical. What do you mean tropical? There's not. I haven't yet spoken about tropical.
It's not clear how exactly you tropicalize that thing in a way that gives you.
Maybe when you think tropical, you need to first embed it. Embed, right? Need to.
I have a map to R4. Let me not compactify it. Let me think of it inside C star cubed or something. No,
Yeah, but then you lose something.
That one will have a bad tropicalization.
Then let's just stay to this context. We can discuss after. Oh, I mean, you ask us, yes, maybe, I mean, yes, because the context, this is the context we are in. Yeah, so this is the essential skeleton. And in order to get a retraction map from the analytic space to the essential skeleton, one can use the idea of Niguez and Xu. So they use the minimal model program. And first step is, so as you already see from the K3 example, if like we have to extend a little bit SYZ, SNC condition. So first we extend Berkovich's construction. This embedding and also retraction map beyond SNC model to DLT models. So DLT models is like a notion in minimal model theory, divisorial log terminal, which allows some mild singularities than SNC. And then by step 2, by the step 2, but the minimal model program implies that there exists a minimal DLT model. And the conclusion, so just allowing mild singularity. You can so assume X is of maximal degeneration. Then, if I write, then I will cover the last. Yes. Yes. That's why we have to allow more singularities. Yeah, it's also minimal. Before blow up, it was minimal. No.
Would the small resolutions have the DLT terminal?
Yes, the small resolution is SNC.
Yeah, but was it also a DLT minimal model?
Yes.
So that's an example of non-uniqueness. For this K-free family, you could either have kept it nodal or you could have taken a small resolution.
So yeah, maybe let me finish the conclusion. Yes. It's just the conclusion. MMP implies existence of minimal DLT model.
Conclusion and X and then something.
Yeah, conclusion. So assume X is of maximal degeneration. I explained on Monday, it means that the monodromy operator is maximally quasi-unipotent. Yes, then first, one can show that so maybe I should say that this maybe so maybe yeah, this is a closed. I think I forgot to write a line in my note, but so first one can say that this equals skeleton Clemens polytope for a minimal DLT model. And as they are equal in this case. So one can deduce from that that this is a closed pseudo-manifold, which just means that it's almost a manifold. So for example, I'll just read. It's the union of all top dimensional simplices, and for any codimension 1 simplex, it's always the boundary of exactly 2 top dimensional simplices, and also like for any 2 top dimensional simplices, we can connect them by a chain of top dimensional simplices. So it's just always almost a manifold.
You mean connected then?
Yes. 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 And then there exists a strong deformation retraction from the analytic space to the skeleton. It's just so orally I give the precise definition, but morally it's just outside the comment.
Connected. So you're saying
It's connected, yes.
Everywhere, what I want to say. Do we know that it's equidimensional locally? So that if I take, let's say that near any point there's a point which lies in a cell of that dimension.
Yeah, it's union of top dimensional cells.
Oh, it is the union of its dimensions. Okay.
So it's almost a manifold, like outside the codimension too. It's a bit long to you just deduce the properties from properties of the minimal DLT model.
There's a notion of combinatorial manifold, right? Where you have to say, along any cell, I look at the star along that cell, and that is like a decomposition of the n sphere.
So moreover,
So here this only holds for codimension 1. With codimension 1 cell, if there's just 2 adjacent top dimensional cells, and there's also no p-sync that just consists of the low dimensional cells sticking out.
Is the link of a higher codimension cell supposed to be a sphere, or can I just have a more?
No, if it were a sphere, you would have a member.
Right.
In this case, you don't assume that. You just assume that you have an
So that's
zero
the
length
defect.
if you have a codimension.
Manifold away from connection.
yeah. So
By the way, I will stop you when you finish writing down.
so I should never write down that.
The parentheses will stay open as long as
You have another question? Oh, yeah. So I'm out of time, but I'm happy that you asked me.
finish first.
I would like to speak just a few sentences more. So yeah, I'm out of time, but I'm happy that you asked many questions. So moreover, one can show, not really in Niguez Xu, that the retraction map we get is an affinoid torus fibration outside the codimension 2. Then Paul will stop me. Yes, and we call this non-archimedean SYZ fibration. So one can look again our running example. We can take a minimal model, for example, the small resolution one, and we get in the small resolution case, the Clemens polytope coincides with the essential skeleton, which is a tetrahedron. And thank you very much for your attention. Yeah, actually, I just finished 2 parts. The third part is about curves, but maybe I move it to the next talk.
Can I ask, when you said that assume X is a maximum degeneration, so you said it was from condition of the monotony?
Yeah.
But how do I formulate that if we start with something?
Oh, locally, one can give a local description, like.
I guess. So if something is defined as a polynomial, I know it means to take the monotony. I just take the actual family of complex numbers and go around in a circle. Take a circle around the monotony.
Oh, you mean?
I'll take that. There's a combinatorial formula for the monotony if you have a SYZ degeneration.
Yeah, that monogamy operator can be defined even for formal In the case of formal schemes, you don't need
So how much further does this go actually from having, something that's locally goes all the way down to points in order to be maximal degenerate? Are there examples of non-maximal degenerate funds that have straight that go down all the way to points?
What was the question?
So concretely, when I think of maximal degeneration, I think that there are pieces that go down all the way to intersections of n things intersecting in a point.
Yes, yes, yes.
Degeneration.
Geometric characterization.
Is that necessary and sufficient? Is that one but not the other? Is that
Yeah, so if we look at the essential skeleton, I mean, that essential skeleton has maximal dimension if and only if the family we start with has maximal degeneration. That one can show.
All right, thank you again.
Thank you.